Why does it matter how much time an algorithm takes to run or how much memory it uses? Well, the answer lies in computational complexity theory. It's the key to ensuring efficient code, and it's a cornerstone of computer science. First, let's delve into the concept of Big O notation. Think of it as a rating system for the efficiency of algorithms. It's a mathematical notation that describes the limiting behavior of a function when the argument tends towards a particular value or infinity. It's a way to express the upper bound of an algorithm's running time or space requirement in the worst-case scenario, hence providing a worst-case guarantee. Consider an algorithm that needs to search for a specific item in a list. If the list has one item, it takes one step to check it. If it has 10 items, it takes 10 steps. This algorithm scales linearly with the size of the input, so we say it has a big O notation of ON, where n is the size of the output. Next, let's talk about time complexity. It's a concept that describes the amount of time an algorithm takes to run as a function of the size of its input. It's essentially a measure of the rate at which the running time of an algorithm increases. As the size of the input increases, time complexity is directly proportional to the number of operations an algorithm performs. Take sorting a deck of cards, for example. A very fast sort might take a time proportional to n log n, where n is the number of cards. A slower sort might take time proportional to n squared. So, the time complexity of the faster sort is O(n) log n, and the slower sort is O(n) squared. Finally, let's discuss space complexity. It refers to the amount of memory an algorithm needs to run. It's a function of the size of the input, just like time complexity. However, instead of measuring time, space complexity measures the amount of space or memory an algorithm requires. For instance, an algorithm that sorts a list of numbers in place without creating a new list has a lower space complexity than one that creates a new sorted list because it requires less memory to perform the sort. To summarize, computational complexity theory is a fundamental tool for analyzing algorithms. Big O notation provides a high-level understanding of how an algorithm performs in the worst-case scenario. Time complexity measures the time an algorithm takes to run, and space complexity measures the memory it requires. Understanding these concepts is crucial for writing efficient code that scales well with increasing input size. So next time you're programming, remember to consider the computational complexity of your algorithms. It could make all the difference in the world.